The second part, how to do multiphysics. And in this part, so we're going to go through the steps that we need to do for doing multiphysics and also the typical elements in solving a multiphysics problem. So this plot shows the typical procedure. Actually, it's similar to a procedure that we will adopt in numerical analysis. The first step is that when we get a multiphysics problem, what we need to do is that we need to identify the problem and also determine which are the major physical fields involved in this problem. For example, we can say that it has heat transfer, thermal field, stress and strain, mechanical field. So these are the two, then we can have two fields. And based on that, we need to establish a mathematical model. And a mathematical model actually just boils down to a bunch of equations. And for this bunch of equations, we have three types. The first type is the governing equation or governing equations. The second type is called auxiliary equations. And the third is the boundary and the initial conditions. So this bunch of equations or equation system usually is complicated to solve, and there's no analytic solution. So what we need to do is that we need to use our tools, that's numerical analysis, to discretize this equation system so we can get a algebraic equation system such as A times U equals B. Then the corresponding process in the computational domain is that, for example, a domain here is just the object or the system that we want to analyze. So inside the domain, we have omega, and the del omega is just the boundary. So what happened by doing a discretization is that we divide the whole domain into multiple different subregions. And for the algebraic equation system, it has a finite size. So we have another size corresponding to the size of the meshed domain. So that's how many cells or how many grid points that we have. So in the above procedure, we can see that we have actually different elements in the implementation. So the first element is the governing equation. So governing equation is just a mathematical equation that describes the distribution and the variation of the dependent variable. And a dependent variable, that's the state variable that we select to represent the status of the system. Sometimes we can choose different state variables to state the system governed by one monolithic physical field, but we may choose one of them as the dependent variable. And here we can take a look at the equation. In this equation, the dependent variable here is U. So the whole equation is used to describe how U will change with some other things. For example, here T is changed with time, and del here, this is the tensor notation. So actually, this can be represent different things. So it can in a typical 2D Artesian space, this could be X and Y. So here U is dependent variable, and we also accordingly we also have independent variable, and here they are T, X, Y, and Z if we in a 3D space. So the governing equation is just like they give out the basic physical laws to define how the physical process will occur. So in this one, you can see that different parts of the governing equation that represents different mechanisms. So on the left, this is accumulation, and the advection, diffusion or dispersion, and then source. So this is the governing equation for a typical transport problem. And auxiliary relationships, actually they are mathematical equations between dependent variables and material property variables. So it could be linear, could be a constant, or it could be nonlinear. And these two plots shows two different types of auxiliary relationships. The first one is a relationship between volumetric water content, and here H means water potential. So this is so-called water retention curve or soil water characteristic curve in porous materials. Here, so it represents a relationship between two state variables. And on the right is a relationship between relative permittivity and suction. So suction is a state variable, and a relative permeability, this is a material property. And the third important element in the implementation of multiphysics is boundary condition. Solving a multiphysics problem is just like, find a solution, a distribution of state variable, which is defined on a domain. In this case, the domain represents the object or the system we want to analyze. So it's an object, that means it's have a finite size, so it has a boundary. So what happens for in the solution process is that actually we can understand it as a interpolation process. So we know the conditions on the boundary, but we don't know the conditions inside the boundary, that's in the domain. So we need to interpolate what we know on the domain to what we want to know inside the domain based on physical laws. So for such a process, we need to know the conditions on the domain. That is usually is given by boundary conditions. For boundary conditions, you can see that mathematically here, they're just about, we just need to define u, here's the value of the state variable, and du dx. So this is the derivative of the dependent variable. And the third significant component is discretization. So we know that a geometric model or a geometry or geometric object represent the system. And here usually we call it domain in numerical analysis. And we know that a continuous domain corresponds to the original mathematical description of the problem. However, there's no analytical solution. So usually we need to use numerical analysis. So what happened in the numerical analysis is that we don't solve the values at every point in this continuous domain, but instead, so we divide the domain into multiple subregions, and then we try to get the solutions for each region. And we can use different resolutions for in the meshing process. So then what happens to the solution is that on the left you can see that this is, let's say this is the true solution. It's true solution, so it's continuously defined in the domain. But if we use numerical analysis, we will get multiple subdomains. So then we will, for solution, we will get a value for each subdomain. So you can see that the solution is discrete. But some of you may say, hey, I used some multiphysics software package, and I get my solution, and I found that I can get the value at every point. So actually, the reason for that is that the value that you get may not be the original solution. It could be a value that is obtained based on the discrete solution using interpolation or extrapolation. So for the equations, if we discretize the equations, so what we will get is something called an algebraic equation system. We use different tools, finite difference method, finite volume method, and finite element method. Sometimes we will get the same algebraic system. Sometimes they could be different. And here I show what is the ax plus c equals b looks like. This is a very typical algebraic equation system for a multiphysical problem. And to solve, so the goal of solving a multiphysics problem is to get the solution to the problem that we just defined. And that is to solve the algebraic equation system in numerical analysis. So we have two major categories of methods. The first method is called direct methods. So for example, we have LU decomposition. And if you use COMSOL, you will see some more different types of solvers, which all of them belong to LU decomposition. And we also have route algorithm. And for another big category is called iterative methods. For this one, a typical example is Jacobi method. And we also have a lot of variations of Gauss-Seidel method. in my opinion, the studies of solvers currently is not a major part of multiphysics because these solvers, they are understood and studied by people from mathematics or computer science. So multiphysics more about how to use these different solvers for solving the numerical solution. So we don't try to derive the solvers directly.
I think I'm falling for you.